Welcome back to The Curious Mind. Whether you are curling up after a long day, watching the shadows lengthen across your room, or simply looking for a quiet place to rest your mind, I am glad you are here. Tonight, we are going to drift toward the edge of what is possible. We are going to explore a dream that has whispered to humanity ever since we first realized that the stars were not merely lights painted on a ceiling, but distant suns, separated from us by oceans of emptiness so vast they defy imagination. The topic for our quiet journey tonight is the ultimate speed limit of the universe, and the tantalizing possibility that we might, just might, be able to break it. But before we race toward the horizon, let us settle in. Take a deep breath. Let the noise of the traffic, the notifications, and the demands of the day fade into the background. Here, there is no rush. There is only the gentle unfolding of ideas. We have all the time in the world to understand the nature of time itself. When you look up at the night sky, it looks peaceful. The stars seem fixed and close, like diamonds scattered on velvet. But you and I know that this stillness is an illusion. Those points of light are roaring infernos, and the blackness between them is a silence deeper than anything we can experience on Earth. It is a silence made of distance. For centuries we thought of space as nothing, a void, an empty stage where we could move as freely as we wished, if only we built a ship fast enough. We imagined that if we simply added more fuel, built bigger engines and pushed harder, we could cross the galaxy in a human lifetime. We dreamed of visiting other worlds, shaking hands with whatever life might exist in the nebula of Orion or the star fields of Andromeda. But then, in the early 20th century, physics whispered a hard truth. It told us that there is a wall, a cosmic speed limit that applies to everything: light, gravity, and information itself. That speed is roughly 186,000 miles per second. It is fast enough to circle the Earth 7 times in a single heartbeat. But on the scale of the cosmos, it is agonizingly slow. At this speed, it takes light 4 years to reach our nearest neighbour star. It takes 100,000 years to cross our own galaxy. And it takes millions of years to reach the next island universe. If this limit is absolute, then the stars are not just far away, they are effectively forever out of reach. We are trapped in our little corner of the dark, looking out at a universe we can see but never touch. It feels like a cage, doesn't it? A glass wall separating us from the rest of creation. For decades, scientists have accepted this. They have bowed their heads to the equations of Albert Einstein, which say that to accelerate a single atom to the speed of light would require infinite energy. Not just a lot of energy, but more energy than exists in all the stars combined. It seemed the universe had put up a do not enter sign on the highway to the stars. But human curiosity is a stubborn thing. We do not like walls, we do not like limits, and so, in the quiet corners of university chalkboards, and in the hushed discussions of theoretical physics, a question has persisted. Is there a loophole? Is there a backdoor in the laws of physics? Recent thoughts, mathematical whispers, suggest that the answer might be yes. Tonight, and over the course of this long, calm journey, we are going to explore how scientists may have found a way around this cosmic limit. We are not talking about breaking the laws of physics, but rather negotiating with them. We are going to talk about bending space, warping time, and using the geometry of the universe itself to slide between the stars. Imagine for a moment that you are standing on the shore of a vast ocean. The water stretches out to the horizon, endless and impassable. You cannot swim across it. You cannot row fast enough to reach the other side before your life ends. That is the speed of light barrier. It is the ocean of distance. But what if you didn't have to cross the water? What if you could fold the shore so that the other side touched your feet? What if you could pick up the patch of water you are standing on and move the water itself, carrying you along with it like a surfer on a wave? This is the heart of the idea we will explore. The realization that while we cannot move through space faster than light, space itself is under no such restriction. Space can stretch, space can contract, And if we can learn to control that stretching, if we can learn to mold the fabric of the dark, then perhaps the speed limit isn't a wall after all. Perhaps it is just a suggestion. As we begin this story, let go of the need to understand the complex mathematics. We do not need equations here, we only need our imagination. Picture the universe not as a hard, empty box, but as a fabric, a soft, pliable, living geometry. We are going to look for the wrinkles in that fabric. We will talk about warp drives, not as science fiction, but as serious geometry. We will talk about the energy needed to power them, energy that behaves in strange, almost magical ways. We will explore the paradoxes that keep physicists awake at night. If you can go faster than light, can you also go back in time? And we will look at the very latest ideas, papers published only recently, that suggest we might not need impossible energy after all. It is a story of human ingenuity refusing to accept that the stars are too far away. It is a story of hope. So, let your eyes grow heavy. Let your breathing slow down. The universe is vast and we are small, but our minds are capable of spanning the infinite. We are about to embark on a voyage that goes beyond speed, beyond distance, and into the very structure of reality. The first step in understanding how to break a rule is to understand why the rule exists in the first place. Why does the universe care how fast we go? Why does nature enforce a speed limit? To answer that, we must look at the nature of light itself. Light is the messenger of the cosmos. It carries the news of what is happening. When you see a star explode, you are seeing news that is thousands of years old. When you look at the sun, though please never look directly at it, you are seeing it as it was 8 minutes ago. There is a delay, a lag. This lag exists because speed is finite. If light travelled instantly, everything would happen at once. Cause and effect would be jumbled. The speed of light is the conductor of the orchestra, ensuring that the violin plays before the cello, that the glass shatters after it is dropped, not before. It is the guardian of causality. If we want to go faster than this guardian, we have to be very, very clever. We have to find a way to move without moving. It sounds like a riddle, doesn't it? Moving without moving. But in the strange world of general relativity, riddles are often the gateway to the truth. So, lie back. Imagine the stars above you. Imagine the immense silence between them. And let us begin to peel back the layers of this silence, to see if there is a way to slip through the dark, faster than a beam of light, and reach the worlds waiting on the other side. To understand how we might one day cheat the speed limit, we must first understand the fence that Albert Einstein built. It is a beautiful fence, sturdy and elegant, constructed from the laws of special relativity. It is not there to punish us. It is there to keep the universe making sense. Let us drift back to the year 1905, a quiet year. The world was moving at the speed of steam trains and telegraphs. But in a patent office in Bern, Switzerland, a young man was dreaming of riding alongside a beam of light. He asked himself a simple question. If I could move as fast as that light beam, what would it look like? Would it freeze? Would the oscillating waves of electricity and magnetism stand still in the air, like a frozen wave in a photograph? It seemed reasonable. If you drive your car alongside a train at the same speed, the train looks stationary relative to you. You can wave to the passengers, and they appear to be sitting still. But Einstein realized that light is different. The equations of electricity and magnetism, written decades earlier by James Clerk Maxwell, said that light must always move. It cannot stand still. A frozen light wave is impossible. It is a contradiction. This led Einstein to a conclusion that shook the foundations of reality. No matter how fast you move, light always moves away from you at the exact same speed. If you're standing still, light leaves you at 670 million miles per hour. If you chase that light in a spaceship moving at 99% of the speed of light, the beam still races away from you at exactly the same speed. It feels wrong to our intuition. We are used to speeds adding up. If I throw a ball from a moving train, the speed of the ball combines with the speed of the train. But light does not obey this arithmetic. Light is the absolute. It is the constant against which everything else is measured. And because light is the constant, everything else must change to accommodate it. This is where the universe begins to bend. If speed is distance divided by time, and the speed of light must stay the same regardless of how you move, then distance and time themselves must be flexible. This is the barrier. This is the weight of motion. As you move faster, time for you slows down. This is not a mechanical failure of your clock. It is a fundamental slowing of reality. Your heart beats slower. Your cells divide slower. Your thoughts crawl. To you, everything feels normal. But to an observer watching you fly past, you are moving in slow motion. At the same time, space behaves strangely. As you speed up, the distance you are traveling shrinks. The universe flattens in the direction of your motion. Space compresses. But the most critical part of this fence, the part that truly stops us from reaching the stars, is mass. Einstein discovered that energy and mass are the same thing. You have heard the famous equation E equals mc squared, energy equals mass. When you push an object, you give it energy of motion, kinetic energy. But because energy and mass are two sides of the same coin, adding energy to an object is like adding a tiny bit of mass. At slow speeds, driving a car, flying a jet, this extra mass is so tiny it is unnoticeable. But as you approach the speed of light, things change. The faster you go, the heavier you get. Not heavier in size, but heavier in resistance. It becomes harder and harder to push you faster. The universe demands a tax on speed. To get to 90% of the speed of light, you need a tremendous amount of energy. To get to 99%, you need even more. As you inch closer, 99.999.99, your mass climbs toward infinity. The energy required to push you that last tiny fraction of a percent becomes infinite. The universe says, you can get close, you can get very, very close, but you can never touch the limit. This is why, in the conventional view of physics, faster than light travel is a fantasy. You would become infinitely heavy. You would need infinite fuel, and time for you would stop completely. It seems hopeless. It seems final. A universe of islands, separated by uncrossable oceans of time and distance. But remember the key phrase, travelling through space. Einstein's special relativity governs objects moving through the fabric of space. It says nothing can overtake a photon in a foot race across the vacuum. But 10 years after special relativity, Einstein gave us general relativity, and that changed the playing field entirely. General relativity tells us that space is not a stage, it is a thing, it is a fabric. And this fabric is not static, it can stretch, it can twist, it can bend. And most importantly, the fabric of space itself is not bound by the speed of light. We know this because the universe is expanding. The galaxies far away from us are receding. If we look at the very distinct galaxies, the ones near the edge of the observable universe, they are moving away from us faster than the speed of light. How is this possible? Are they breaking the law? No, they are not moving through space. The space between us and them is stretching. It is new space being created, billowing out like bread dough rising in an oven. The galaxies are just riding along. Nothing in physics prevents space itself from expanding or contracting faster than light. The speed limit applies to the ants crawling on the rubber sheet, not to the stretching of the sheet itself. This is the crack in the wall. This is the ray of hope. If we could control that stretching, if we could grab the fabric of space-time and manipulate it at will, we wouldn't have to accelerate our ship at all. We wouldn't face the problem of infinite mass. We wouldn't experience the crushing dilation of time. Instead of pushing the ship through the water, we would move the water. Imagine a bubble, a small quiet bubble of flat, normal space. Inside this bubble sits our spaceship. The ship is at rest, the engines are off. The astronauts are floating, drinking their coffee, feeling no acceleration, no G-forces. But outside the bubble, space is doing something wild. Behind the ship, space is expanding explosively, pushing the bubble forward. In front of the ship, space is contracting, pulling the bubble in. The ship is surfing. It is riding a wave of distorted geometry. The bubble itself moves through the universe faster than light, carrying the ship with it. But inside the bubble, locally, the ship isn't moving at all. It is bypassing the law of special relativity, because it isn't moving relative to its local space. This idea, known as the warp drive, was once pure science fiction. It was the stuff of television shows and paperback novels. But in 1994, a physicist named Miguel Alcubierre sat down and did the math. He wrote out the geometry for exactly such a bubble. He found that it was consistent with Einstein's equations. General relativity allowed it. The math worked. It was a moment of electric possibility. The Alcubierre drive became a legitimate topic of scientific study. But there was a catch, a massive towering catch. To make space expand behind you and contract in front of you, you need gravity. But gravity, as we know it, only pulls, it attracts. Mass tells space to curve inward. To make space expand, to push, you would need something that creates repulsive gravity. You would need a substance with negative mass. Negative energy. We have never seen a chunk of negative mass. We don't know if it can exist in the quantities needed. For years, this requirement seemed to doom the warp drive to the realm of theoretically possible, but practically impossible. But science does not stand still. New papers are being written. New solutions are being found. The dream of the warp drive is evolving. We are finding ways to lower the energy requirements. We are exploring shapes of bubbles that might not need negative energy at all. We are beginning to see the faint outlines of a path through the barrier. So, as we rest here in the quiet of the cosmos, understand that the weight of motion is real. The barrier is high, but the fabric of the universe is more flexible than we ever dared to dream, and we are just beginning to learn how to weave it. We are standing on the edge of the shore, looking at the water, and realizing that perhaps, just perhaps, we can teach the waves to carry us home. We left off standing on the shore of the cosmic ocean, imagining a way to move the water instead of swimming through it. It is a beautiful image, but to turn it into reality, we have to look at the loom upon which the universe is woven. We have to speak the language of the weaver, which is geometry. As we settle deeper into this idea, remember that for a long time, we thought of space as emptiness, a void where things simply happened. But we learned that space is not just a stage, it is a participant. It is a living fabric that bends, stretches, and ripples. This is the central lesson of general relativity. Matter tells space how to curve, and space tells matter how to move. Usually, when we think of this curvature, we think of gravity. We imagine the sun sitting in a dimple of space-time, and the Earth rolling around it, following the curve like a marble on a bowl. In that scenario, the curvature is gentle. It is a valley that guides us. But to build a warp drive, to travel faster than light, we need to do more than just follow a valley. We need to grab the landscape and twist it into a shape that nature does not build on its own. Think of the warp bubble we mentioned earlier. Inside this bubble, where the spaceship sits, space is flat and calm. We call this locally flat. It is like being in a falling elevator where gravity seems to vanish and you float in perfect stillness. In that small region, the laws of physics look exactly as they do in empty space. You could pour a cup of coffee and it would not slosh against the side of the cup. You would feel no speed, no acceleration, no crushing force pressing you into your seat. But the walls of this bubble are where the violence happens. The geometry of the universe is being asked to do something extraordinary. In front of the ship, we need space-time to contract rapidly. We need it to shrink, pulling the destination toward us. Behind the ship, we need space-time to expand, pushing the departure point away. This is not moving through space, it is surfing on space. And because the ship is inside a protective shell of flat space, it never locally exceeds the speed of light. It is the bubble itself that moves, carried by the expanding and contracting fabric. Since space-time can stretch and bend without limit, the bubble can sweep across the stars at speeds that would make a beam of light look like it was standing still. The question that has haunted scientists is, what kind of architect can build such a structure? In Einstein's equations, The geometry of the universe is determined by the distribution of matter and energy. If you put a planet here, you get a gravity well. If you put a star there, you get a deeper well, and time slows down. To get the specific complex shape of a warp bubble, a shape that pushes and pulls simultaneously, you need a very specific arrangement of energy. For decades, the math said this arrangement was impossible for us to build. It required negative energy, a substance that pushes gravity away rather than pulling it in. Normal mass, like stars and planets, curves space in a way that creates attraction. It creates a dip in the fabric. To get the expansion we need behind the ship, we would need a hill in the fabric. And hills, in the language of gravity, require energy that weighs less than nothing. This was the stalemate. The geometry was perfect, but the bricks needed to build it didn't seem to exist. We were like architects with blueprints for a floating castle, but only heavy stones to build with. But recently, the conversation has shifted. A new wave of physicists has gone back to the drawing board, or rather, back to the equations. They have begun to ask if there are other ways to fold the fabric. They are looking at complex, twisted arrangements of normal positive energy that might mimic the effect of a warp drive without breaking the laws of thermodynamics. They are studying solitons. A soliton is a self-reinforcing wave that maintains its shape as it travels. Think of a rogue wave in the ocean that travels for miles without breaking. In the context of space-time, a soliton would be a packet of curvature that moves through the universe, carrying its contents with it. If these new calculations are correct, we might not need the impossible negative energy after all. We might be able to construct a warp bubble using the gravity of normal matter. If, and it is a big if, we can arrange it in a geometry so precise, so intricate, that it tricks space into flowing around us. It would be a geometry of immense subtlety. Instead of a brute force engine blasting fire out of the back, imagine a ship surrounded by a shell of ultra-dense matter, spinning and flowing in currents that grab the fabric of space-time and twist it. Remember that rotating mass drags space-time along with it, a phenomenon called frame dragging. We know this is real. We have measured it around Earth. Now imagine scaling that up. Imagine using the frame dragging effect, not just to twist space slightly, but to create a flowing river of geometry that carries us forward. The ship becomes a needle, threading through the cosmic cloth, slipping between the threads of space and time. This is the new hope, that the barrier of light speed is not a wall, but a puzzle. And the pieces of that puzzle are made of the same stuff as the stars, just arranged in a pattern we are only just beginning to understand. If geometry provides the map, then energy provides the fuel. And here lies the second great mountain we must climb. Even if we can design a warp drive that requires only normal positive energy, the amount of energy we are talking about is staggering. In the early days of these calculations, the news was sobering. The math suggested that to create a warp bubble, just a few meters across, you would need more energy than exists in the entire observable universe. It was a theoretical triumph, but a practical absurdity. Later, as the equations were refined, the requirement dropped. It went from the universe to the mass of Jupiter, then down to the mass of the moon. Now, with the latest ideas about solitons and optimized shapes, the energy requirements are plummeting further. Some models suggest we might be able to do it with the energy equivalent of a planet, or perhaps even a large asteroid. This is still an immense, almost inconceivably large number. But it is no longer infinite. And in science, the difference between infinite and finite is the difference between impossible and merely difficult. We must remember that energy and mass are two sides of the same coin. When we speak of the energy to power a warp drive, we are really speaking about the ability to curve space. And we know that mass bends space. The Earth bends space enough to keep the moon in orbit. The sun bends space enough to hold all the planets. But the bending required for a warp drive is sharp. It is intense. We are not talking about the gentle slope that guides a falling apple. We are talking about a canyon so steep that it slides us across the galaxy. To create such a curvature, the density of energy must be extreme. This brings us to a fascinating realization about the universe. Gravity is actually a very weak force. Think about it. You can lift a cup of tea with your arm, defying the gravitational pull of the entire Earth. The geometry of space-time is stiff. It takes a massive amount of matter to create even a small curve. To bend it enough to travel faster than light, we would need to concentrate energy in ways that we currently only see in the hearts of black holes. However, there is a nuance here. The new research suggests we might not need to bend space deeply if we bend it cleverly. Instead of a deep well, perhaps we can create a series of ripples, a rhythmic pulsing of the fabric that builds up speed over time. Think of a swing set. If you push once, you don't go very high. But if you push in rhythm, adding a little bit of energy at exactly the right moment, you can swing higher and higher. Perhaps the warp drive of the future will not be a sledgehammer that shatters the speed limit, but a resonator that hums at the right frequency, coaxing the stiff fabric of space-time into motion. We know that space-time is elastic. It can vibrate. Gravitational waves are proof of this, ripples stretching and squeezing space as they pass. These waves carry energy. If we could learn to generate and focus these waves, to create a standing wave of curvature around our ship, we might find that the energy cost is not about raw power, but about precision. It is a shift from brute force to harmony. The universe is a tapestry, and we are learning that you do not tear the tapestry to move across it. You slide along the weave. There is also the question of where this energy comes from. In the depths of space, there are no gas stations. But the cosmos itself is awash in power. Stars pour out light and solar wind. Black holes emit jets of plasma. The vacuum itself might hold secrets we have yet to tap. If we can solve the energy problem, if we can bring the cost down from a galaxy to a star and then to a reactor, then the door opens. The silence between the stars stops being a barrier and becomes a highway. It is a long road ahead. We are still in the phase of scribbling on chalkboards, but the fact that we are talking about how much energy, rather than it is impossible, is a profound shift. We are negotiating with the laws of physics. We are asking the universe, what is your price? And the universe, in its quiet, curved language, is beginning to answer. It tells us that the speed of light is a limit for things moving in space, but space itself has no master. The fabric is free to dance, and if we can pay the cost, we can dance with it. So, as you drift in the quiet of your evening, imagine that the stillness around you is not empty. It is a reservoir of potential. The very air, the room, the distance to the moon, it is all made of this flexible, hummable geometry. We are small, yes, but we are learning to touch the strings of the cosmos, and one day we may play a note that carries us to the stars. We have spoken of bending space and gathering the energy of stars, but there is a shadow that follows us on this journey. It is a shadow cast not by an object, but by the very nature of reality. If we succeed in outrunning light, we must ask ourselves a question that borders on the philosophical. What happens to time? In our everyday lives, time feels like a steady river. It flows at one pace, carrying us all from the past into the future. But we have already learned that this is an illusion. Time is not a universal clock ticking in the background. It is a dimension, woven together with space into a single fabric called space-time. And just as space can stretch and curve, time can slow down and speed up. We know, thanks to the quiet insights of relativity, that time is personal. It beats differently for everyone. A clock on a fast-moving satellite ticks slightly slower than a clock on your nightstand. A clock near a massive pyramid or a mountain runs at a different rhythm than one at sea level. The universe lets every corner breathe at its own pace. But this flexibility has a rule, a cosmic chaperone that keeps history in order. That rule is the speed of light. It acts as the ultimate referee, setting the fastest possible pace for cause and effect. Nothing can travel faster than light because, in the eyes of relativity, moving through space is also trading motion through time. Imagine a flash of light in the dark. It spreads outward in a sphere. If you draw that expansion through time, it looks like a cone rising upward, a light cone. Everything inside that cone is your future. Everything outside it is elsewhere, forever out of reach. This is nature's way of enforcing order, ensuring that the glass breaks after it falls, not before. It is the gentle rule of causality. Now, imagine our warp ship. We are wrapped in a bubble of geometry, surfing a wave of contracting and expanding space. We are moving from Earth to a distant star faster than a beam of light could make the journey. We are stepping outside the light cone. Here is where the dream of the stars meets the paradox of the clock. If you can outrun light, the equations suggest you might also be able to outrun time itself. In some configurations of faster-than-light travel, it becomes theoretically possible to arrive at your destination before you left. You could, in principle, turn your ship around and return to Earth to see yourself packing your bags. This is the grandfather paradox, the headache of time travel. If you can change the past, does the future exist? Does the universe allow such disorder? Many physicists believe that the cosmos has a chronology protection mechanism, a hidden law that prevents closed time loops. They suspect that if you tried to build a time machine, the vacuum itself would resist, energy would build up, the warp bubble would destabilize, or probability would shift to stop you. Perhaps the universe protects its history just as it protects its speed limit. However, the warp drive offers a curious loophole. Because the ship inside the bubble never locally moves faster than light, it is sitting still while space moves. It might avoid the worst of these paradoxes. The time inside the bubble flows normally. You drink your tea, you read your book, you age 1 hour for every hour that passes. You are not feeling the crushing time dilation of near-light speed travel, where thousands of years might pass outside while you experience only days. Instead of travelling into the future, by slowing down your own time, you are stepping sideways across the geometry. You are taking a shortcut. A geodesic is the shortest path between 2 points in curved space-time. Usually, that path is a straight line or an orbit, but if we warp space, we create a new geodesic, a tunnel through the distance. When we arrive at the star Proxima Centauri 4 years early, we are not necessarily in the past. We are just there now, in a now that light hasn't reached yet. We are disconnected from the visual history of Earth, outracing the image of our departure. If we looked back with a powerful telescope, we would see ourselves 4 years ago, preparing to leave. We would be ghosts watching our own history unfold, separated by the immense lag of light. It is a strange, lonely thought. To travel faster than light is to become untethered from the shared now of the universe. You become a traveller not just in space, but in a separate causality. Yet the universe may be more forgiving than we think. Just as it allows black holes to twist time into infinite loops near their hearts, it may allow us to slide through these loopholes without breaking the story of existence. We might find that causality is not a rigid chain, but a web, capable of stretching without snapping. So, as you lie there, listening to the silence of the room, think of time not as a straight arrow, but as a vast, shimmering ocean. We are usually drifting with the current, pushed forward by the steady tick of seconds. But the warp drive is a ship that learns to sail against the wind, to cut across the waves, and perhaps to find islands of time we never knew existed. The paradoxes are scary, yes, but they are also beautiful. They tell us that reality is richer, stranger, and more intricate than a simple clockwork mechanism. And in the end, perhaps the only way to understand time is to break free from it, to drift on the waves of a curved and responsive universe. We have spoken of the map of geometry and the river of time, but every journey needs fuel. We established earlier that the energy required to bend space-time is immense. Originally thought to be more than the universe contains, now perhaps whittled down to the size of a planet or a star. But even the energy of a planet is hard to carry in a fuel tank. If we are to sail the stars, we cannot bring the wind with us. We must find it out there in the deep dark. This brings us to one of the most profound secrets of modern physics. Empty space is not empty. For centuries, we thought of the vacuum as a void, a nothingness, a place where absolutely nothing exists. But quantum mechanics, the theory of the very small, has shown us that this is untrue. If you could zoom in on empty space, past the atoms, past the dust, down to the tiniest scales imaginable, you would see a storm. The vacuum is alive. It is seething with energy. In the quantum world, particles are constantly popping into and out of existence, borrowing energy from the vacuum and paying it back in a fraction of a second. These are called virtual particles. They appear in pairs, dance briefly, and annihilate each other. It happens everywhere, all the time, in the space between your eyes, in the gaps between stars, inside the atoms of your body. This constant jittery activity creates what physicists call vacuum energy, or zero-point energy. It is the background hum of the cosmos. It means that even in the deepest silence, the universe is singing. We know this energy is real because we can measure its effects. One famous demonstration is the Casimir effect. If you take two uncharged metal plates and place them extremely close together in a vacuum, they will be pushed together. Not by gravity, not by magnetism, but by the vacuum itself. The sea of virtual particles outside the plates is stronger than the sea inside the narrow gap, creating a pressure that pushes them inward. It is a tiny force, barely a whisper, but it proves that the nothing of space has weight. It has substance. Now, recall our problem with the warp drive. To build the bubble, to expand space behind the ship, and contract it in front, we initially thought we needed negative energy. We needed something that pushes gravity away. Here is where the magic of the quantum vacuum comes in. In certain conditions, this vacuum energy can behave like the negative energy we need. It can create a pressure that stretches space. In fact, we believe this is already happening on a cosmic scale. We call it dark energy. It is the mysterious force that is currently accelerating the expansion of the universe. It is pushing galaxies apart, stretching the cosmic web. It acts like a repulsive gravity, an elastic tension in the fabric of space-time itself. So the fuel we need, the exotic space-stretching energy, might not be something we have to manufacture. It might be the very ocean we are sailing through. Imagine a ship that doesn't carry fuel, but harvests it from the texture of space. A ship that taps into the quantum fluctuations of the vacuum, amplifying the natural jitter of reality to create the warp bubble. It would be like a sailboat catching the wind, or a hydroelectric dam using the flow of a river. We would be using the latent energy of the universe to reshape the universe. This connects the very large, general relativity and gravity with the very small quantum mechanics and vacuum fluctuations. It is the meeting place of the two great theories. The warp drive becomes a machine that weaves these two worlds together. Of course, tapping into this energy is not easy. It is like trying to catch a wave in a teacup. The energy density of the vacuum is low in open space, or perhaps high, but balanced in a way we cannot easily access. Some theories suggest the energy is enormous, enough in a coffee mug to boil the oceans, but it cancels itself out so perfectly we don't feel it. The challenge for the future sleepy scientists, the engineers of the 22nd or 23rd century, will be to find a way to tip this balance, to create a region around the ship where the vacuum energy is manipulated, polarized, or concentrated. If we can do that, the cost of the stars changes completely. We wouldn't need to crush a planet to power our engines. We would just need to learn how to resonate with the empty space around us. It is a comforting thought, isn't it? That we are not alone in a cold, empty void. We are swimming in a sea of potential. The emptiness is full. The silence is a song. And the distance that separates us from the stars is made of the very stuff that might one day carry us to them. As we drift further into this idea, the universe feels less like a barrier and more like a partner. It has provided the map, curvature, the vehicle, the bubble, and perhaps even the fuel, the vacuum. It is simply waiting for us to understand the instructions. So let the concept of the living vacuum settle in your mind. The air around you, the dark outside your window, it is all shimmering with invisible possibility, waiting for the moment we learn to set it in motion. As we drift deeper into the night, let us turn our minds to the shape of the vessel that might carry us across the dark. We have spoken of energy and of time, but what does this ship actually look like? Not the metal bolts or the ceramic hull, but the invisible shape that surrounds it, the architecture of the warp bubble itself. For a long time, the only shape physicists could imagine was the one Miguel Alcubierre first drew in 1994. It was a simple spherical shell. Inside, a flat region for the traveller. Outside, a chaotic storm of expanding and contracting space. It was elegant, but it was hungry. It demanded that impossible negative energy we spoke of earlier. But imagine if you could fold a piece of paper into a paper airplane. The flat sheet doesn't fly well, but if you crease it just right, it glides. Theoretical physicists have been trying to find the right creases for space-time. Recently, a researcher named Eric Lentz proposed a new shape. Instead of a simple sphere requiring exotic negative fuel, he looked for a shape that could be built from positive energy, the kind of energy we know exists, the kind found in plasma, in radiation, in the magnetic fields of stars. He found it hidden in the geometry of hyperbolic curves. It is a shape that looks less like a bubble and more like a diamond, or perhaps a complex, multi-layered soliton. Imagine a structure made of distinct currents of curvature, weaving over and under each other like a Celtic knot. In this new design, the space-time isn't just pushed and pulled, it is guided. The Lentz soliton arranges the gravitational fields in a way that balances the forces naturally. It uses the density of normal matter, immense concentrated density, to create the wave. It is a breakthrough because it moves the warp drive from the realm of magic physics to engineering physics. We no longer need a substance that defies the laws of nature. We just need to learn how to compress and shape the energy we have. Of course, the engineering is still beyond us. To build this diamond of gravity, we would need to manipulate mass energy on a scale that makes a nuclear reactor look like a candle. We might need to create states of matter that are super dense, spinning at relativistic speeds, flowing in precise superconducting loops to generate the necessary gravitational field. But picture the beauty of it, a ship encased not in metal shielding alone, but in a shield of curved light and gravity, a geometric diamond sliding through the ink of space. This new shape also helps with another problem, the debris. Space is not truly empty, it is filled with tiny dust grains and gas. If you fly through them at superluminal speeds, they could hit your bubble with devastating force. But a shaped bubble, a soliton with the right aerodynamic geometry, might deflect them. It might let the dust slide around the warp field like water around the bow of a boat. So the ship of the future is not a brute force rocket. It is a work of art. It is a sculpture of gravity, designed to slip through the universe with the minimum of resistance. It is a shape that respects the medium it travels through. And this brings us a sense of peace. We are not fighting the universe to conquer it. We are learning its secret language of shapes. We are discovering that the lock on the speed limit has a key, and that key is geometry. The diamond shape, the soliton, the warp bubble. These are just our first clumsy attempts to cut that key. Now, let us step inside. Let us leave the chalkboard and the equations behind and imagine the experience. You are an astronaut in this future vessel. You have engaged the drive. The soliton field has formed around you. The universe outside is warping. What does it feel like? The most surprising answer is that it feels like nothing. If the bubble is working perfectly, there is no sense of movement. There is no roar of engines, for the drive interacts with the fabric of space, not the air. There is no vibration, for the bubble isolates you from the friction of the cosmos. You could balance a coin on its edge, and it would not fall. This is the principle of free fall that Einstein loved so much. Inside the bubble, you are weightless, or perhaps held in a gentle artificial gravity, but you feel no acceleration. You are safe in the eye of the hurricane. But while your body feels stillness, your eyes would see something extraordinary. As the bubble accelerates, the light from the stars ahead of you begins to change. We know that when you move toward a light source, the waves get squashed. They turn blue. This is the Doppler shift. At low speeds, you wouldn't notice. But as you approach the speed of light, the stars in front of you would shift from yellow and white to a piercing blue, then to violet. Eventually, they would disappear from human sight entirely, shifting into the ultraviolet and then into X-rays. The darkness ahead would become a source of invisible, high-energy radiation. Behind you, the opposite happens. The stars you are leaving recede. Their light stretches out. They turn orange, then deep red, then infrared, and finally fade into the radio spectrum. The universe behind you goes dark. So, sitting in the captain's chair, you would see a ring of light. The stars that are to your side, neither directly ahead nor behind, would drift forward. This is called aberration. It is like driving in rain. The rain seems to come from the front, even if it is falling straight down. As you go faster, this effect grows extreme. The entire visible universe would appear to concentrate into a bright glowing ring ahead of the ship. A starbow. It would be a rainbow of stars, banded by colour. The inner edge, near the centre of your vision, would be blue and violet. The outer edge would be red. And in the very centre, a dark spot where the radiation is too intense for your eyes. It is a view no human has ever seen. A navigation console made of light itself, but there is a deeper strangeness. If you are travelling faster than light, you are outrunning the image of your own ship. If you could somehow look out a side window, past the distortion of the bubble, you would be seeing a universe that is aging differently. And what of the connection to home? Radio waves travel at the speed of light. If you are moving faster than they do, you are cutting yourself off from communication. You cannot send a message back to Earth saying, "I am safe," because you would arrive at the destination before the message does. You are in a silence that is absolute. You are a traveller in a bottle, drifting across an ocean where sound cannot carry. This isolation might seem frightening, but in the quiet of the night, it can also be comforting. It is the ultimate solitude. Just you, the hum of the ship, and the beautiful, distorted light of the cosmos. There is a serenity in the centre of the bubble. The violence of the warping space is just a few meters away, tearing the fabric of reality. But where you sit, the tea is still hot, the air is still calm, and the only sign of your impossible journey is the ring of fire guiding you to the stars. It reminds us that even in the midst of extreme power, there can be a quiet centre, a place of rest. The sleepy scientist finds comfort here, in the eye of the storm, watching the universe paint a new picture on the canvas of the night. We are resting in the centre of the bubble, watching the starbow, that magnificent ring of light that marks our path through the dark. It is a peaceful image, isn't it? A silent ship gliding through a distorted cosmos. But there is a subtle warmth creeping into our quiet sanctuary, a complication that reminds us that nature does not give up her secrets easily. To understand this new challenge, we must look at the walls of our vessel again. The warp bubble is not made of glass or steel. It is made of extreme gravity. It is a shell where space-time is falling faster than light. In many ways, the front edge of our bubble behaves like the event horizon of a black hole. It is a point of no return for information trying to reach us from the outside. And just as black holes are not truly black, our warp bubble is not truly cold. Decades ago, the physicist Stephen Hawking taught us that event horizons glow. They emit a faint radiation, born from the quantum jitter of the vacuum. Pairs of particles, one matter, one antimatter, pop into existence near the edge. If one falls in and the other escapes, the horizon appears to shine. For a black hole, this glow is incredibly faint, but for a ship travelling faster than light, smashing through the quantum vacuum, the effect is different. We are ploughing through the sea of virtual particles. The horizon in front of us is scrubbing against the fabric of the universe. Calculations suggest that inside the bubble, this friction would create heat. As we accelerate, the horizon ahead begins to glow, not just with the blue shifted light of stars, but with a thermal radiation generated by the warp field itself. We call this the Unruh effect, a close cousin to Hawking radiation. Imagine sitting in your captain's chair. The room begins to warm. The silence is still absolute, but the air grows thick. The faster you go, the hotter the horizon becomes. At low warp speeds, it might be a gentle warmth, like sunlight on your face, but as you push deeper into the superluminal, that warmth could turn into a roasting fire. This is the thermodynamic cost of warp drive. We are trying to isolate ourselves from the universe, but the universe is leaking in. The quantum vacuum is resisting our passage, turning the friction of our geometry into searing energy. To survive this, our ship would need shielding unlike anything we have ever built. We might need refrigerators that pump heat out into a place where time flows backward, or materials that can reflect the quantum glow. Or perhaps we will have to accept a speed limit within the speed limit, a maximum velocity determined not by power, but by how much heat the crew can survive. There is another hazard waiting in the dark, one that is even more tangible than quantum heat. The vacuum of space is not perfectly empty. It is dusted with hydrogen atoms, tiny grains of sand, and wisps of cosmic gas. When a normal spaceship hits a grain of dust at normal speeds, it leaves a tiny pit in the hull. But we are not moving at normal speeds. We are gathering space-time. As our bubble sweeps forward, contracting the space in front of us, we are also sweeping up everything that lives in that space. The hydrogen atoms, the dust, the stray photons. They get caught in the gravitational wave. They cannot escape. They pile up on the leading edge of the bubble like snow on a plough. But they don't just sit there. The intense gravity of the warp field accelerates them. It crushes them. It energizes them. A single atom of hydrogen swept up by a warp drive could be transformed into a high-energy cosmic ray, vibrating with incredible power. For the duration of the journey, these particles are trapped in the shockwave ahead of us. They are a growing storm of radiation, riding the bow of our ship. Inside the bubble, we are safe, protected by the flat geometry. But the shell around us is becoming a bomb of accumulated energy. This creates a profound problem for navigation. We are effectively flying blind behind a wall of fire. Our sensors cannot see through the distortion and the radiation storm. We cannot use radar, for the radar beams would be trapped by the bubble. We cannot look out the window to steer, for the stars are twisted into a meaningless ring. We would have to navigate by math alone. Before we leave, we would have to calculate the entire journey. We would have to aim the ship with perfect precision, knowing exactly how space curves, where the stars are, and how long to hold the warp. Once the drive is engaged, we are bullets fired in the dark. We cannot turn, we cannot adjust. We must trust the trajectory. It requires a new kind of faith, a faith in the clockwork of the cosmos. We are surrendering control to the geometry we have created. And what if we drift? What if a gravitational wave from a distant black hole nudges our path by a fraction of a degree? Over a distance of light years, that tiny nudge could make us miss our destination by trillions of miles. We might emerge from warp in the empty void between stars, lost in the deep dark with no fuel to return. So, the sleepy scientist of the future must be a master of maps. They must know the terrain of the galaxy better than they know the lines of their own hands. They must account for the drift of stars, the rotation of the galaxy, and the subtle breathing of the interstellar medium. But let us not be discouraged by the heat or the dust. These are engineering problems. They are the friction of the road, not a collapsed bridge. We solve them with thicker hulls, with magnetic deflectors that sweep the dust away before the bubble catches it, and with cooling systems that hum in the background, keeping our tea at the perfect temperature. The important thing is that we are moving. We are carrying our fragile biology through the hostile furnace of the vacuum, protected by a bubble of our own design. We are turning the hazards of the universe into the parameters of our journey. As you rest here, imagine that protective shell. Imagine the layers of insulation, the magnetic fields, the cooling loops, all working in harmony to keep the small, soft interior safe. It is a metaphor for life itself, isn't it? We build shelters, we wear coats, we create safe spaces to protect the delicate flame of our consciousness from the cold indifference of the world. The warp ship is just the ultimate expression of that human need for safety amidst the storm. The journey has been long, though inside the bubble, it may have felt like only days or weeks. We have slept while the galaxy streamed past us in a blur of blue and violet. We have trusted the math. We have endured the heat of the horizon. Now, the clock on the dashboard ticks down to 0. It is time to stop. Stopping a warp drive is not like hitting the brakes on a car. In a car, friction slows you down. In space, there is no friction. And remember, our ship isn't really moving in the traditional sense. Space is moving us. To stop, we have to unravel the geometry. We have to smooth out the wave. We must tell the space behind us to stop expanding and the space in front of us to stop contracting. We have to dissipate the immense energy of the soliton field, letting the fabric of space-time snap back to its normal flat state. This is the most dangerous moment of the voyage. Recall the storm of particles we gathered. The hydrogen, the dust, the light, all swept up on the leading edge of our bubble, energized to terrifying levels. For the entire journey, they have been trapped there, unable to escape the gravitational grip of the warp field. When we turn off the drive, that grip vanishes. In an instant, all that accumulated energy is released. The particles, now moving at nearly the speed of light, are hurled forward in a concentrated beam. It is a shockwave of gamma rays and high-energy plasma, a warp boom that screams across the finish line. If we are not careful, this shockwave could be devastating. If we aim our ship directly at the planet we want to visit, and we drop out of warp too close, that beam of radiation could scour the surface of the world. We could arrive as destroyers, sterilizing the very destination we came to explore. This is the doomsday arrival scenario. It sounds grim, but it teaches us manners. It tells us that we cannot just barge into a new solar system. We must be polite. We must approach obliquely. The pilots of the future will not aim for the planet. They will aim for the empty edge of the solar system, far from any life. They will drop out of warp in the deep freeze of the Oort cloud, releasing their shockwave into the harmless dark. Then they will use conventional engines, good old-fashioned chemical or ion rockets, to cruise the final distance on a slow, gentle arc. It adds a poetic slowness to the end of the journey. We cross the galaxy in a flash, defying time and distance, but the final steps must be taken slowly, with humility. We must knock on the door before we enter. As the bubble dissolves, the view changes. The ring of fire, the starbow, expands and breaks apart. The colours separate. The violet shifts back to blue, then to yellow. The darkness behind us fills in with stars. The universe snaps back into its familiar shape, and there, hanging in the void, is a new sun. Maybe it is a red dwarf, glowing like a dying ember. Maybe it is a binary star, two suns dancing in a gravitational embrace. Maybe it is a blue giant, fierce and bright. We have crossed the ocean. But there is a haunting realization as we look at this new star. We are seeing it as it is now. Back on Earth, looking through telescopes, astronomers see this star as it was 4 years ago, or 10 or 100. The light hitting Earth is old news, but we have skipped the line. We are standing in the present moment of this distant world, and if we turn our telescopes back toward Earth, what do we see? We see our home as it was in the past. If we travelled 100 light years, we see the Earth of 100 years ago. We see a world without the internet, without satellites, perhaps in the midst of a past war or a past celebration. We see our ancestors walking streets that have since been paved over. We are ghosts haunting the future, looking back at a past that is still travelling through the dark in the form of light. This is the emotional weight of breaking the cosmic limit. We have severed the connection to our own time. We are now living in a different now than everyone we ever knew. If we send a radio message saying, "We arrived," that message will travel at the speed of light. It will take years to get back. By the time they hear our voice, we will be older or gone. The warp drive connects space, but it fragments time. It creates pockets of humanity separated by silence. Yet, there is beauty in this separation. It makes every arrival a new beginning. We are not just tourists. We are pioneers stepping onto a shore that has never felt a human footprint. We are expanding the definition of home. We will have to build new societies, new cultures, based on the rhythm of these new worlds. We will have to learn to live with the silence of the long delay. As the ship coasts toward the new planet, the engines hum a low, steady note. The adrenaline of the arrival fades. The crew unbuckles. They float to the windows, watching the alien clouds turn beneath them. They are tired. The journey through the geometry was effortless for their bodies, but the realization of what they have achieved is heavy on their minds. They have cheated the speed of light. They have walked through the wall, and in doing so, they have proven that the universe is not a cage. It is a vast, open field, waiting for us to find the courage to run across it. We have spent our time drifting among the stars, imagining ships the size of buildings, riding waves of gravity. It is a grand vision, filled with the roar of silent energies and the colours of the starbow. But the path to the infinite often begins in the smallest of places. Before we can build a vessel that spans the galaxy, we must first learn to bend space in a room. So let us leave the bridge of the starship for a moment and descend to Earth. Let us drift into a quiet, sterile laboratory. The air is cool and still. The lights are dim. In the centre of the room sits a table floating on cushions of air, isolated from the vibrations of passing trucks or shifting tectonic plates. On this table lies a maze of mirrors and lasers. This is an interferometer. It is a device designed to measure the geometry of space with exquisite precision. The scientists here are not trying to send a person to Mars. They are trying to detect a nudge, a tiny, almost imperceptible shift in the path of a laser beam. They are asking a humble question: can we create a warp bubble that is microscopic? The idea is that if we can create a tiny ring of negative potential energy, perhaps using high-voltage capacitors or superconducting rings, we might be able to curve space just enough to disturb the light. We are not trying to surf a wave yet. We are just trying to prove that the water can ripple. For years, researchers at places like NASA's EagleWorks lab have been working on this. They fire a red laser through a split path. One half of the beam travels through the device, the potential warp generator, and the other half travels through empty air. When the beams recombine, they create an interference pattern, a series of light and dark stripes. If the space inside the device curves, even by a fraction of a hair's width, the pattern will shift. It is like trying to see if the wind is blowing by watching a single blade of grass shiver. It is frustrating, delicate work. The signals are often lost in the noise of the world. A door closing down the hall, or a temperature change of 1 degree, can ruin the experiment. But the dream persists. The hope is that one day the laser will jump. The pattern will move, not because of a vibration, but because the distance the light travelled actually changed. It would mean we have compressed space. It would be the Wright brothers moment for warp drive, not a flight across the Atlantic, but a hop of a few feet on a sandy beach. A proof that the impossible is merely a matter of engineering. In these quiet labs, the universe is being interrogated. We are knocking on the door of the laws of physics, listening for the faintest echo of an answer. It reminds us that the grandest journeys start with the smallest steps, and that the thunder of a warp drive begins with the whisper of a laser in the dark. Sometimes the universe answers when we aren't even asking the question. Discovery is not always a straight line. Often it is a stumble in the dark that lands us in a new room. Recently, a team of scientists funded by DARPA was studying something entirely different. They were looking at Casimir cavities, microscopic spaces between metal plates where the vacuum energy behaves strangely. They were trying to design cooler, more efficient microchips, or perhaps new kinds of thrusters. They were not looking for faster than light travel, but when they analysed the data from one of their nanostructures, they saw something that made them pause. The energy distribution in their tiny cavity didn't just look random, it looked familiar. When they ran the numbers, the pattern of energy matched the geometry of a warp bubble. It was not a full warp drive, it was not moving, it was a nanoscale warp bubble that had formed spontaneously in the math of their device. It was as if they had been trying to build a toaster and accidentally built a model of a jet engine. This accidental discovery sent a ripple of excitement through the quiet community of theoretical physicists. It suggested that the specific geometry needed to bend space, the toroidal negative energy density shape, was not just a fiction on a chalkboard. It was a physical state that could exist in the real world, created by the interplay of electric fields and the quantum vacuum. Imagine the wonder of that moment. You are looking at a spreadsheet of numbers or a heat map of energy density and realizing that you are staring at the blueprint for the stars. The structure they found is incredibly small, far smaller than a bacterium. It cannot carry a ship. It cannot even carry an atom. But it exists. It is a proof of concept provided by nature itself. It tells us that the vacuum is willing to form these shapes if we provide the right boundary conditions. Now the goal is to scale up. Can we take this microscopic accident and build it on purpose? Can we make it the size of a coin? Then a car, then a ship? We are still far away from that reality, but the psychological barrier has been cracked. We know that the unobtainium needed for warp drive, the negative energy density, is something we can generate in the lab using the Casimir effect. We have moved from if to how. So as you rest, think of that tiny, accidental bubble, a microscopic distortion in the fabric of reality, sitting unnoticed on a silicon chip. It is a seed, and like all seeds, it holds the potential of a forest. It is a quiet promise that the road to the stars is open, if only we can learn to pave it. We have spent much of our journey talking about surfing, about riding a wave of distorted space, but there is another way to cheat the cosmic limit, a way that doesn't involve speed at all. Imagine, if you will, that the universe is a sheet of paper. You are a tiny ant standing on one edge, and you want to reach a crumb of sugar on the opposite edge. To you, the paper is flat and endless. The journey is long. You have to walk every inch of the distance. But you and I, looking down from above, know that the paper is flexible. We can pick it up, we can bend it, we can bring the two edges together until they touch. Suddenly, the ant doesn't have to walk across the paper. It can simply step from one edge to the other. The distance has vanished. This is the concept of the wormhole. In the formal language of physics, it is called an Einstein-Rosen bridge. It is a tunnel that connects two distant points in space-time, creating a shortcut through the higher dimensions of the universe. While the warp drive is about moving the space around you, the wormhole is about changing the topology of the universe itself. It is about stitching two places together. If warp drive is a surfboard, a wormhole is a door. Einstein and his colleague Nathan Rosen discovered this possibility in the math of relativity back in 1935. They realized that the deep gravity well of a black hole could, in theory, connect to another well elsewhere. A tunnel could form between them. For a long time, this was just a mathematical curiosity, a what if. But as we look for ways to cross the galaxy, the wormhole offers a tempting alternative. With a warp ship, you still have to travel the distance. Even at 10 times the speed of light, crossing the Milky Way takes 10,000 years. But a wormhole is instant. You step in here, near Earth, and you step out there, near the Andromeda Galaxy. One step, zero time. It sounds perfect, it sounds like magic, but like the warp drive, the wormhole demands a price. The throat of the tunnel, the hallway connecting the two doors, is inherently unstable. Gravity wants to pinch it shut. The moment you try to step inside, the tunnel collapses, leaving you crushed in a singularity. To keep the door open, to keep the walls of the tunnel from crashing down, we need a scaffold. And once again, we return to the need for exotic matter or negative energy. We need a substance that pushes the walls apart, holding the throat open against the crushing weight of gravity. But we have seen that the quantum vacuum might provide this energy. We have seen hints in the Casimir effect. Perhaps, just perhaps, a civilization advanced enough could weave a web of negative energy to prop the door open, creating a permanent subway system for the cosmos. Imagine a network of these gates, great shimmering rings floating in orbit around stars. They would be silent, dark, perhaps distorting the starlight behind them like a lens. They would be the ports of the galaxy, no engines required, no fuel tanks, just a step across the threshold. It is a beautiful dream, one that turns the vast, lonely universe into a neighborhood. It suggests that distance is not an absolute law, but a variable geometry. It suggests that if we are clever enough, we can fold the dark until the stars are right beside us. Let us drift closer to this imaginary gate. Let us picture what it would be like to travel through a wormhole. In science fiction, this is often a chaotic ride. Lights flashing, the ship shaking, a kaleidoscope of colours. But the physics suggests something much quieter, much more surreal. As you approach the mouth of the wormhole, you would see a sphere. It would look like a crystal ball floating in space. Inside this ball, you wouldn't see the reflection of your own ship. You would see the destination. If the other end of the wormhole is orbiting a blue star in the Pleiades cluster, then the sphere in front of you would be filled with the light of that blue star. It is a window cut into the fabric of reality. As you drift closer, the sphere grows. It fills your vision, and then you pass through the surface. You are now in the throat, the tunnel. Here the geometry is twisted. If you looked out the side window, you wouldn't see stars. You would see the distorted, streaking light of the universe passing by the tunnel walls. You are moving through a region where space is folded on itself. The journey might be instantaneous, or it might take a few minutes, depending on the length of the throat, but it would be smooth. Gravity here is balanced. You are falling freely toward the exit, and then you emerge. The sphere recedes behind you, but now it holds the image of Earth. You are thousands of light years from home, yet you can turn around and see your sun, small and yellow, floating in the glass ball of the wormhole. The connection is live. You could shine a laser through the wormhole and see it hit a satellite back on Earth instantly. There is no time lag through the tunnel. This creates a dizzying realization. If you look at Earth through the wormhole, you see it as it is now. But if you look at Earth through the normal void of space, with a telescope, you see it as it was thousands of years ago. You have two views of home, the immediate present through the door, and the ancient past through the void. This geometry is fragile. If we build these bridges, we must treat them with care. We cannot let them vibrate too much. We cannot let too much mass pass through at once, or the energy balance might tip and the throat might pinch off, severing the link forever. It implies a future where travel is a ritual, a careful, calculated passage. We would not be conquerors rushing through. We would be pilgrims, stepping softly through the needle's eye. The wormhole is the ultimate victory over the silence. It destroys the isolation of the speed of light. It allows us to hold hands across the galaxy. As you lie in the dark, imagine these tunnels threading through the invisible bulk of the universe. Like the roots of a great tree connecting distant patches of soil. We cannot see them yet. We cannot build them yet. But the math says the roots are there. We just have to find the shovel. For now, the stars remain far away, But in the mind of the sleepy scientist, the distance is folding, the map is wrinkling, and the door is waiting to be opened. We have imagined the wormhole as a door, a shimmering sphere that lets us step from Earth to the edge of the galaxy in a single heartbeat. It is a beautiful image, standing there, like a gateway in the garden of the cosmos. But a door does not simply appear. It must be built, it must be woven, and the thread used to weave this connection might be found in the strangest behaviour of the smallest particles in the universe. To understand where a wormhole comes from, we must leave the scale of planets and stars and drift down into the subatomic. We must look at a phenomenon that Albert Einstein famously called spooky action at a distance. This phenomenon is quantum entanglement. Imagine two particles, let us call them electrons, born from the same burst of energy. Because of their shared origin, they are linked. Their properties are tied together like two dancers, moving in perfect synchronization, even if they cannot see each other. If one spins up, the other must spin down. They are a single system, separated by space. Now imagine we separate them. We keep one here on Earth and send the other to the far side of the universe, billions of light years away. According to the rules of quantum mechanics, they remain connected. If we measure the electron on Earth and find it spinning up, the electron on the far side of the cosmos instantly snaps into the state of spinning down. There is no delay, no signal travels between them. It happens faster than light. It happens instantaneously. It is as if the space between them does not exist. For decades, physicists struggled with this. It defied the rule that nothing travels faster than light. How does the second particle know what the first one did? What connects them across the void? Recently, a profound idea has emerged from the quiet corners of theoretical physics. It is an equation of ideas, simple enough to whisper, but deep enough to drown in. It is called ER equals EPR. ER stands for Einstein-Rosen bridges, wormholes. EPR stands for Einstein-Podolsky-Rosen, quantum entanglement. The idea suggests that these two things are actually the same. It proposes that the spooky connection between two entangled particles is actually a tiny, microscopic wormhole linking them through the fabric of space-time. The particles are not sending signals to each other faster than light. They are touching. They are connected by a tunnel so small we cannot see it, a thread of geometry stitching them together. If this is true, then the universe is not just an empty box filled with lonely particles. It is a vast, tangled web. Every time atoms interact and become entangled, they thread a tiny wormhole between them. The fabric of space-time itself might be sewn together by these billions upon billions of quantum stitches. Now, let us scale this up to the size of our dreams. If a tiny wormhole connects two electrons, what happens if we entangle something massive? What if we take two black holes, the densest, heaviest objects in nature, and entangle them? Imagine creating two black holes in a laboratory. A terrifying thought, but we are safe in our imagination. We entangle them perfectly, just like the electrons. Then we separate them. We send one to the Andromeda Galaxy and keep one here. According to the theory of ER equals EPR, the microscopic wormholes connecting their individual particles would merge. They would combine, growing larger and wider until they formed a single, massive tunnel connecting the two black holes. The spooky action of the quantum world would become a physical bridge in the macroscopic world. The thread would become a hallway. This realization changes everything. It tells us that wormholes are not just random accidents of geology that we have to hunt for. They are built from the fundamental relationships of matter. To build a gate to the stars, we do not need to punch a hole in the universe with brute force. We need to create a profound connection. We need to entangle our location with the destination. It gives a romantic hue to the physics. It suggests that to reach the stars, we must first become intimate with them. We must share a quantum history. We must link our fate to theirs. But there is a catch, a safety rail on this cosmic bridge. Even if we entangle two black holes and create a tunnel, the standard laws of physics say the tunnel is not traversable. It is too long, or it pinches shut too fast. You might jump into the black hole on Earth, and your friend might jump into the one in Andromeda, and you might meet in the middle, but you could never escape to the other side. You would be trapped together in the darkness. To make the bridge walkable, to turn the thread into a road, we still need that magic ingredient we spoke of earlier, negative energy. We need to prop the throat open. We need to stiffen the walls of the quantum tunnel so that we can pass through without being crushed. But the path is clear. The connection is possible. The universe allows it. So as you lie in the quiet, imagine the invisible threads connecting you to the room, to the air, to the world outside. We are all made of particles that have interacted with countless others since the Big Bang. In a poetic sense, we are all entangled with the cosmos. We are all connected by tiny, invisible bridges to the furthest reaches of time and space. The silence between the stars is not empty. It is filled with these invisible strings. And one day, the sleepy scientist believes, we will learn to pull on those strings, to widen them, and to slide across the distance as easily as a thought travels from one side of your mind to the other. If we accept that a wormhole is a tunnel, a shortcut that burrows from one part of the universe to another, we are forced to ask a question that sounds almost like a child's riddle. What is the tunnel going through? If I dig a tunnel through a mountain, I am going through rock. If I dig a tunnel under the ocean, I am going through the earth. But if I dig a tunnel through space itself, what is outside of space? To answer this, we must expand our minds into a new direction. We must think about dimensions. We live in a world of 3 dimensions: length, width, and height. We move left and right, forward and backward, up and down. To us, this is everything. It is the whole box. But the existence of a wormhole implies that there is a higher dimension, a space outside of our space, through which the tunnel cuts. Physicists call this the bulk, or sometimes hyperspace. To picture it, imagine a sheet of paper floating in the air. This paper is a 2-dimensional world. Flat creatures live on it. They can move forward, backward, left and right, but they have no concept of up or down. To them, the paper is the entire universe. Now imagine we bend the paper into a U shape. The 2 edges of the paper are now close together in the air, but to the flat creatures, they are still miles apart along the surface. If one brave flat creature could step off the paper, moving through the air, it could hop from one edge to the other instantly. That air, the space between the folded paper, is the bulk. It is the higher dimension that makes the shortcut possible. For us, the universe is the paper. We are trapped on this 3-dimensional brain, short for membrane, floating in a higher dimensional ocean. We cannot see the bulk. We cannot point to it. Up into the bulk is a direction we cannot point, just as the flat creature cannot point upward. But a wormhole is a tube that leaves our sheet of paper, travels through the bulk, and reconnects with the paper somewhere else. When we step into that shimmering sphere, we are technically leaving our universe. We are taking a detour through a dimension that is usually forbidden to us. What is out there in the bulk? It is a silence deeper than the vacuum. In our universe, the vacuum is filled with fields, electromagnetic fields, the Higgs field, gravity. But the bulk might be truly empty of the things we know. Light, for example, is trapped on our brain. Photons are stuck to the paper. That is why we cannot see into the 4th dimension. Our light cannot travel there. If you were inside a wormhole with glass walls, looking out into the bulk, you might see absolute perfect blackness. No stars, no galaxies, just the raw, unformed potential of higher geometry. Or perhaps it is not empty. Some theories of cosmology suggest that there are other brains, other universes, floating in the bulk alongside ours, like sheets on a clothesline, drifting in the cosmic breeze. Maybe, just maybe, gravity is the only thing that can leak off our brain. This would explain why gravity is is so weak compared to the other forces. A magnet can pick up a paperclip against the pull of the entire Earth because electromagnetism stays here, concentrated, while gravity bleeds away into the higher dimensions, diluting its strength. If we travel through a wormhole, we are swimming in that gravity ocean. We are taking a shortcut through the space between spaces. This idea changes the way we feel about the cosmos. It suggests that our observable universe, vast as it is, might be just a thin skin on something much larger. It suggests that the cosmic limit of light speed is only a limit on the skin, not in the deep water. Navigating the bulk would be the ultimate art of the sleepy scientist. It would mean calculating a path not through the stars, but around them. It would mean diving into the hidden depth of reality to surface in a new harbour. The dangers here are abstract but profound. If the wormhole collapses while you are in the bulk, do you fall back into our universe? Or do you get stranded in the nothingness between universes, a sailor lost in an ocean with no shore? Or worse, could you drift into the wrong universe entirely? Could you exit the tunnel and find yourself in a cosmos where the laws of physics are slightly different, where atoms do not hold together, or where time runs backward? These are the whispers of the high theorists, the bedtime stories of physics. They remind us that we are small, huddled on our little raft of 3 dimensions, but they also tell us that there is more to discover. As you rest, let the walls of your room fade away. Imagine that outside is not just the street or the garden, but a direction you cannot see, a direction leading to the bulk. The wormhole is our window into that greater world. It is the promise that we are not trapped on the surface of reality, but that we can, with enough wisdom, learn to dive. The silence of the bulk is not a lonely silence, it is a waiting silence. It is the breath held before the plunge, and as we drift towards sleep we can dream of the day we learn to breathe in that deep, dark ocean. We have lingered long on the edge of the wormhole, peering into that shimmering sphere that promises a shortcut across the galaxy. It is a tempting vision, a step, a breath, and then a new sky. But as any architect will tell you, the most beautiful bridges are often the most fragile. And the bridge we are trying to build across the bulk is made of something far more delicate than steel or stone. It is made of the very limits of quantum law. To understand why this bridge is so precarious, imagine digging a tunnel through dry, loose sand. As long as you are digging, pushing the sand aside with your hands, the hole exists. But the moment you pull your hands away, the weight of the sand rushes in. The tunnel collapses, it fills up, gravity wins. In the case of a wormhole, the sand is the fabric of space-time itself. The throat of the wormhole, the narrow tunnel connecting Earth to Andromeda, is under immense pressure. The gravity of the universe wants to pinch it shut. In fact, the equations of general relativity predict that a natural wormhole would snap close so quickly that not even a beam of light could make it through before the door slammed. It would be a bridge that crumbles the moment you step on it. This is where the concept of the glass bridge comes in. We need a material to line the tunnel, to hold back the crushing weight of the sand. We have spoken of negative energy and exotic matter before, but here, the requirements are even more strict. We need a continuous beam of this energy, threading the entire length of the wormhole, acting as a pillar of repulsion. But nature has a rule about this. It is called the quantum energy inequality. Think of it as a bank. The universe allows you to borrow energy, to create a patch of negative energy, which is like a debt, but it demands that you pay it back, and quickly. The more energy you borrow, the faster you must repay it. If we try to line our wormhole with enough negative energy to let a spaceship pass through, the bank of the universe might intervene. The debt might become too large. The quantum fluctuations might rebel, creating a pulse of radiation that destroys the tunnel just as we try to open it. So, the sleepy scientist faces a dilemma. We can build the bridge, but the laws of physics might prevent us from crossing it. We might be able to create a wormhole that stays open for a nanosecond, or one that is too small for a human, but a stable, human-sized gate might be forbidden by the fine print of reality. Unless, of course, we change the design. Recent papers have suggested that we don't need to line the whole tunnel. Maybe we just need to prop open the entrances. Or maybe we can use the spin of the wormhole itself to keep it open. A spinning black hole flings matter away from it. Perhaps a spinning wormhole would fling the walls of the tunnel apart, using centrifugal force to fight gravity. Imagine a tunnel that is rotating wildly, a vortex in the bulk. To enter it, you would have to match its spin, spiraling into the throat like a leaf caught in a whirlwind. It would be a dizzying, graceful maneuver. You would not walk across this bridge, you would dance across it. There is also the question of what happens if the bridge breaks while you are on it. If the exotic matter fails or the spin slows down, the throat pinches off. The connection between Earth and Andromeda is severed. But you, the traveller, are still inside. You would be trapped in a baby universe. When the wormhole snaps, the tunnel doesn't just disappear. It buds off. It becomes a closed bubble of space-time, floating in the bulk, disconnected from everything else. You would be the master of your own tiny cosmos, a sphere of space perhaps only a few miles wide, drifting forever in the silence of the higher dimensions. It is a terrifying thought, but also a strangely peaceful one. To be completely cut off from history, to exist in a pocket of reality that belongs to no one but you. But let us assume the bridge holds. Let us assume we solve the stability problem. We still have to deal with the view. Inside a wormhole, light behaves in ways that defy intuition. Because gravity is pushing the walls apart, it also acts like a lens that defocuses light. If you looked down the tunnel, you wouldn't just see the destination. You would see rings of distorted starlight from the universe you are leaving. The walls themselves might be transparent, revealing the grey nothingness of the bulk, or they might be mirrors, reflecting your own ship back at you infinitely. You would see 1,000 copies of yourself trailing behind you like echoes in a canyon. Navigating this hall of mirrors would require a calm mind. You would have to ignore the illusions, the phantom ships, the twisted stars, and keep your eyes on the single, true light at the end of the tunnel. It is a journey of focus. The glass bridge requires you to trust the path, even when the walls seem to be closing in. It requires you to believe that the math is stronger than the sand. And as we rest here, safe on the solid ground of Earth, we can appreciate the solidity of our own space. We do not have to fight to keep our room from collapsing. Gravity is our friend here, holding us to the bed, holding the air to the planet. But out there, in the dark, we will have to fight for every inch of open space. We will have to build our own stability. The wormhole is a testament to the fact that connection is hard work. It takes energy to keep the door open. It takes effort to bridge the gap. But the view from the other side, the view of a new galaxy rising in the sky, is worth the risk of the crossing. If the wormhole is a bridge that connects 2 points instantly, and the warp drive is a surfboard that rides a wave, then there is a third option, a more permanent solution, one that requires patience, but offers a reward that could last for civilizations. We call it the Krasnikov tube. Imagine you are laying a train track. As you lay the rails, you travel forward. You cannot reach the destination before the tracks are down. You have to do the hard work of crossing the distance at normal speeds, or perhaps near light speeds, carrying the materials with you. But once the track is laid, the train can move backward and forward effortlessly. A Krasnikov tube is a distortion of space-time that you leave behind you as you travel. Imagine a spaceship equipped with a powerful engine, moving at nearly the speed of light toward a distant star. As it moves, it modifies the space-time metric in its wake. It smooths out the path. It creates a superhighway behind it. The journey to the star takes a long time. If the star is 10 light years away, it takes 10 years, from the perspective of Earth, to get there. There is no cheating the journey on the way out. The crew ages. They sleep in cryopods. They wait. But once they arrive, the tube is complete. The tube is a permanent tunnel of warped space connecting Earth and the star. Inside this tunnel, the rules of travel are different. The geometry is configured so that a return trip back to Earth takes almost no time at all. This solves one of the biggest headaches of faster-than-light travel, the causality paradox. With a warp drive, you can technically arrive before you left. With a Krasnikov tube, the timeline is strictly ordered. You spend 10 years building the road to get there. You arrive 10 years in the future. But you can travel back home instantly, arriving 10 years after you left. You can never return to the past. You can only return to the time you left, plus the time it took to build the road. You cannot kill your grandfather. You can only visit your grandchildren. It is a subway system for the galaxy. Imagine a future where humanity has sent out paving ships, immense, automated vessels that crawl through the dark, laying these tubes of distorted gravity. They are the cosmic construction workers. They spend centuries travelling to the Pleiades, to Betelgeuse, to the Orion Nebula. Behind them, they leave a shimmering wake, a corridor of silence. Once the paver ship arrives, the line is open. We can then board a transit pod on Earth, slip into the tube, and slide to Orion in a matter of days or weeks. We would not be warping space ourselves. We would be riding the groove left by the paver. This idea changes the sociology of space travel. It means that the first generation of travellers are sacrifices. They are the ones who spend their lives in the dark, laying the track so that their children can travel the stars freely. They are the cathedral builders, working on a structure they will never fully enjoy, so that the future can be vast. The Krasnikov tube also has a beautiful stability. Unlike a wormhole, which wants to collapse, the tube is just a shape of space. It doesn't need to be propped open with intense continuous energy in the same way. It is a modification of the vacuum that sits there, like a valley carved by a glacier. However, it is invisible. If you looked at the space between Earth and the star, you wouldn't see a giant pipe, you would just see space. But if you flew your ship into that specific corridor, you would suddenly find that your engines are more efficient, that the distance seems to melt away. You would feel the current of the tube taking you. Of course, there are hazards. What if something drifts into the tube? An asteroid, a comet? The tube is a gravity corridor. Anything that falls in might be accelerated to relativistic speeds, turning into a missile that shoots down the tracks toward Earth or the colony. So, the subway would need maintenance. We would need track sweepers, robots that patrol the length of the tube, clearing debris, ensuring the geometry remains smooth. It paints a picture of a galaxy that is not wild but industrialized, a galaxy crisscrossed with invisible highways, maintained by machines, used by commuters. It makes the universe feel a little less like a frontier and a little more like a city of light years. And there is a quiet comfort in that, the idea that we can terraform the vacuum itself, that we can crave paths through the wilderness of physics. The first journey is hard, the first journey is long, but the road home is short. As you drift to sleep, think of those tracks being laid in the dark, the silent paver ships moving away from us, threading the stars together. We might not see the network completed in our lifetime, but we can dream of the day when the sky is not a barrier, but a map of open roads. The silence between the stars is just waiting for the first train to blow its whistle. We have spoken at length about the grand ships that might one day carry us across the void, vessels of diamond and gravity, sliding through the dark. But there is a part of us that wonders if we might reach the stars without ever leaving the ground. Before we send our bodies into the deep cold, perhaps we can send our voices. The universe, for all its vastness, is currently a place of slow conversations. If we were to detect a signal from a civilization in the center of the galaxy today, and we sent a reply immediately, it would take 25,000 years for our hello to reach them. A conversation where the pause between greeting and response is longer than recorded human history is not a conversation, it is archaeology. To truly connect with the cosmos, we need a signal that moves faster than light. We need a messenger that ignores the speed limit. And in the dusty corners of theoretical physics, there is a ghost story about just such a particle. It is called the tachyon. The name comes from the Greek word tachys, meaning swift. In the mathematics of relativity, the tachyon is the mirror image of ordinary matter. You and I, the planets and the stars, are made of tardions, particles that move slower than light and require infinite energy to reach the speed of light. Light itself is made of luxons, particles that have no mass and must move at exactly the speed of light, never slower, never faster. But the tachyon lives on the other side of the mirror. It is a particle that is born moving faster than light. For a tachyon, the speed of light is not a ceiling, it is a floor. It cannot slow down to the speed of light. To do so would require infinite energy. Just as we are trapped moving slower than the limit, the tachyon is trapped moving faster. If these ghosts exist, they inhabit a world where everything is reversed. As a tachyon loses energy, it speeds up. As it gains energy, it slows down toward the barrier of light. A tachyon with zero energy would move at infinite speed, crossing the entire universe in a single instant. Imagine if we could harness this. Imagine an antenna capable of modulating a beam of tachyons. We could build what science fiction authors call an ansible, a device for instantaneous communication. You could sit in a control room on Earth and fly a rover on Mars in real time, with no lag. You could talk to an astronaut circling Betelgeuse as if they were sitting in the next room. The galaxy would shrink from a vast, lonely expanse into a single, connected village. The silence between the stars would finally be broken, but the universe is protective of its silence. The existence of tachyons brings us back to the headache of time. Because they move faster than light, tachyons can, in certain frames of reference, appear to move backward in time. If I send a tachyon signal to you, and you are moving away from me at high speed, the math says you might receive the signal before I send it. You could then send a reply that reaches me before I originally spoke. This creates the anti-telephone paradox. If I can send a message to the past, I could warn myself not to make a mistake. I could send the stock market results to yesterday. I could disrupt the chain of cause and effect that holds reality together. Because of this, most physicists believe that tachyons do not exist. They are seen as a mathematical glitch, a sign that something is wrong with the theory rather than a real object in nature. They are the ghosts in the machine of relativity, visible in the equations, but forbidden in the world. However, the sleepy scientist knows that forbidden is a word that history often revises. Perhaps tachyons do exist, but they cannot interact with normal matter, passing through us like shadows. Or perhaps the universe has a way of preventing the paradoxes, a chronology protection that scrambles any message sent to the past, turning it into noise. Maybe the static we hear on our radios, the background hiss of the universe, is filled with the voices of the future, trying to speak to us in a language we cannot yet hear. For now, the tachyon remains a dream, but it reminds us that our understanding of speed is symmetrical. There is the slow world and there is the fast world, and the wall between them is the speed of light. We are looking for a door in that wall. Whether that door is a warp bubble, a wormhole, or a ghost particle, the search continues. As you drift, imagine a universe where the news travels instantly, where a star being born in the Andromeda galaxy is felt in your heart the moment it happens. A universe where there is no lag, no delay, only the immediate, shared experience of existence. It is a beautiful thought to hold in the dark. We have talked about the map, the vehicle, and the signal, but we must return to the most primal need of any traveller, fire. To warp space, to punch tunnels through the bulk, or even to power a civilization that spans the stars, we need energy sources that dwarf anything we have ever built. We burn coal, we split atoms, we capture sunlight. These are the campfires of a young species. They are enough to keep us warm on Earth, but they are not enough to bend the geometry of the cosmos. To go to the stars, we need to bottle the stars. Or perhaps we need to bottle something darker. There is a concept in astrophysics called the Kugelblitz. It is a German word meaning ball lightning, but in physics, It refers to something far more intense. A black hole made of pure energy. Usually, black holes are formed from the collapse of massive stars. They are made of crushed matter, but Einstein taught us that energy and mass are equivalent. If you concentrate enough energy in a small enough space, gravity will take over. Imagine a future where we build a sphere of gamma-ray lasers, millions of them, all pointing inward at a single microscopic point. We fire them all at once. The light pulses converge. The energy density at the center becomes so high that space-time creates a knot. It collapses. For a brief fraction of a second, we have created a black hole. Not from matter, but from light. This artificial black hole would be tiny, perhaps smaller than a proton, but it would be incredibly hot. Stephen Hawking showed that black holes radiate energy, and the smaller they are, the hotter they burn. A black hole the size of a proton would shine with the power of a nuclear power plant. This is the Kugelblitz. It is the ultimate battery. We could encompass this tiny monster in a shell of mirrors or magnetic fields, feeding it a trickle of matter to keep it from evaporating completely. In exchange, it would give us a continuous stream of Hawking radiation, pure high-efficiency energy. We could use this energy to power the warp drive. We could use it to propel a starship to near-light speeds. We would essentially be mounting an artificial star on the back of our ship. The Kugelblitz drive solves the problem of fuel weight. Chemical rockets are heavy. You have to lift the fuel to move the fuel. But a black hole is compact. It is the densest energy storage allowed by the laws of physics. A ship powered by a Kugelblitz could travel for decades without refueling. But imagine the danger. You are flying through the void with a captive singularity on board. If the containment field fails, the black hole doesn't just stop working. It explodes. A microscopic black hole left unchecked would radiate away all its remaining mass in a blinding flash of gamma rays, vaporizing the ship instantly. It is a ride on the back of a tiger. This fragility adds a layer of reverence to the technology. The crews of these ships would be guardians of the fire in the most literal sense. They would be tending to a microscopic seed of destruction, coaxing life and motion from it. It suggests that our future among the stars will not be one of dominance, but of balance. To wield such power, we must have the wisdom not to drop the bottle. We are not there yet. Our lasers are too weak, our mirrors too imperfect. But the physics is sound. The Kugelblitz is not magic. It is just the extreme edge of the rules we already know. As you lie there, think of the energy trapped in the room with you. The light in the bulb, the heat in the air. Now imagine compressing it, squeezing it down until it punches a hole in reality. That is the power of the sleepy scientist's future. We are learning to light fires that will not just warm a cave, but illuminate the galaxy. We are learning to turn the violence of gravity into the engine of exploration. And in the silence of the night, that engine is humming, waiting for us to turn the key. The black sun is waiting to rise. We have built a ship powered by black holes and guided by the geometry of solitons. It is a vessel of immense power, capable of crossing the void between stars. But there is a subtle danger we have yet to fully address, one that arises not from the technology of the ship, but from the nature of the road itself. We often think of space as a vacuum, a perfect emptiness. But this is an approximation. The space between the stars, the interstellar medium, is filled with a thin mist of hydrogen atoms, helium, and tiny grains of cosmic dust. In the quiet drift of a normal orbit, these particles are harmless, ghosts that pass through the night. But when you move at the speeds we are dreaming of, when you approach the speed of light or bend space to bypass it, these ghosts become bullets. Imagine driving a car through a gentle summer rain. At 30 miles per hour, the water beads on your windshield. Now imagine driving that car at thousands of miles per hour. The water would strike with the force of concrete. For a starship moving at relativistic speeds, a single atom of hydrogen hitting the hull carries the energy of a highly charged particle beam. A grain of dust the size of a grain of sand would strike with the force of a small nuclear explosion. If we were to fly unprotected, our beautiful diamond ship would be eroded, pitted, and eventually vaporized by the very emptiness it seeks to cross. To survive, we must carry our own atmosphere. We must build a shield not of metal, but of force. Nature has already solved this problem for us. Look at the Earth. We are constantly bombarded by the solar wind, a stream of charged particles screaming from the sun. If they hit the atmosphere directly, they would strip it away. But Earth has a magnetic field. Deep in its iron core, a dynamo spins, generating a vast, invisible bubble of magnetism that surrounds the planet. When the solar wind hits this bubble, it is deflected. It flows around the Earth like water around a stone, reconnecting on the far side. The only sign of the violence is the aurora borealis, the northern lights, where a few particles leak through and paint the sky with green and violet fire. Our starship must be a miniature Earth. It must carry a magnetosphere. Engineers envision wrapping the ship in a loop of superconducting wire, miles long, perhaps trailing behind the vessel or embedded in its structure. When charged with electricity, this loop would generate a magnetic field of immense strength. As the ship plows through the interstellar medium, this magnetic field would reach out ahead of us, ionizing the gas and dust before it touches the hull. It would grab the charged particles and sweep them aside, creating a safe harbor in the center of the storm. We would be flying inside a magnetic cocoon. To an outside observer, the ship would look like a comet, preceded by glowing bow shock where the shield meets the interstellar wind. The friction of our passage would create a continuous aurora, a shroud of shimmering plasma that lights the way. But there is a catch. Magnetic fields work well against charged particles like protons and electrons. They do not work against neutral atoms or rocks. A non-magnetic dust grain would slip right through the field and strike the hull. So, the shield must be complex. It might need a plasma layer, a cloud of ionized gas held in place by the magnets, acting as a physical buffer to vaporize dust grains on impact, turning them into charged plasma that can then be swept away. It is a chaotic, violent process happening just a few miles ahead of the ship's nose. But inside, in the quiet of the crew quarters, you would be safe. You would be protected by the same physics that protects the Earth from the sun. There is something poetic about this. To leave our home and survive the cold of the dark, we have to bring the essence of our home with us. We have to wrap ourselves in the same invisible armor that sheltered life for billions of years. We are not just travelers, we are world builders, carrying a spark of planetary physics into the deep void. And as you rest, imagine that protective glow, a ship wrapped in northern lights, sliding silently through the galaxy, parting the sea of stars with a shield made of pure force. We have a ship, we have fuel, and we have a shield. But who is steering? At the speeds we are contemplating, human reflexes are tragically slow. It takes a nerve impulse, a fraction of a second to travel from your eye to your brain, and another fraction to travel to your hand. In that heartbeat of delay, a starship moving at the speed of light would have travelled nearly 200,000 miles. If a sensor detects an obstacle, a rogue asteroid, a fluctuation in the warp field, a drift in the magnetic shield, no human pilot could react in time. By the time you saw the red light on the dashboard, the disaster would have already happened. By the time you thought to bank left, the ship would be dust. To navigate the relativistic ocean, we must surrender the wheel. We must hand the ship over to a mind that thinks as fast as light itself. The starship of the future will not just carry a computer, it will be a computer. Its hull, its engines, its sensors will be the body of an artificial intelligence designed for one purpose: survival in the deep dark. This AI would not be like the chatty assistants we have today. It would be a silent, hyper-aware consciousness, integrated into every bolt and circuit. It would monitor the health of the warp bubble billionths of a second at a time. It would taste the interstellar medium through the magnetic shield, adjusting the field strength to match the density of the gas ahead. It would be a predictive navigator, because the ship might be moving faster than the sensors can see. If we are in a warp bubble, the AI must rely on probability and maps. It must calculate the location of every star, planet and dust cloud for light years around, updating its model of the universe in real time. It would be like a grandmaster chess player, but instead of moving pieces, it is moving a vessel through a four-dimensional maze, anticipating moves that haven't happened yet. But there is a deeper role for this machine mind. The journey to the stars is long. Even with a warp drive, a trip to the other side of the galaxy could take months or years. A trip to another galaxy could take generations. Humans are fragile. We get bored, we get depressed, we forget, we age. The AI would be the keeper of the mission. It would be the historian, the librarian, and the psychologist. It would watch over the crew while they sleep in cryostasis, monitoring their heartbeats and their dreams. It would maintain the ship's systems for decades of silence, repairing itself with robotic arms, tending to the hydroponic gardens, keeping the air sweet and the water pure. It would be the genius loci, the spirit of the place. There is a strange intimacy in this relationship. The crew would have to trust this machine with their lives completely and utterly. They would be children in the care of a silicon guardian. And what happens if the mission changes? What if the destination star turns out to be unstable? What if the ship receives a signal from Earth cancelling the trip? The AI would have to make decisions. It would have to weigh the safety of the crew against the objectives of the mission. It would need ethics. This is the great challenge of the sleepy scientist's future. Not just building a faster engine, but building a wiser mind. We need to code a conscience into the machine. We need to teach it the value of the fragile, soft creatures sleeping in its belly. Imagine the ship drifting in the void, light years from any sun. The crew is asleep, the corridors are dark and silent, but the walls are awake. Data streams through the optical fibers like thought. The ship is watching the stars, calculating, adjusting, protecting. It is the ultimate partner. We provide the dream, the curiosity, the reason to go. The machine provides the vigilance, the patience and the speed. Together, biological and artificial, we become a new kind of organism, one capable of surviving the infinite. We have designed a vessel that can withstand the fires of the warp and a mind that can navigate the labyrinth of the stars. But we must now turn our gaze to the most fragile component of this entire endeavour, the passenger. The human body is a miracle of biology, but it is a soft, wet, breathing miracle designed for the gentle rhythms of Earth, not the crushing silence of the void. Even with a warp drive that cheats the cosmic speed limit, the galaxy is vast. A journey to the other side of the Milky Way, even at 10 times the speed of light, would take thousands of years. A trip to a nearby star might take weeks or months. For a machine, a month is just a data stream. For a human, it is a long time to be trapped in a tin can. There is also the problem of resources. A waking human is a hungry engine. We need food, water, oxygen, and entertainment. We produce waste. We consume air. To keep a crew of 100 people alive and happy for a 5-year voyage requires a ship the size of a city, filled with farms and water recycling plants. The mass of all that life support makes the ship heavy, and in the tyranny of the rocket equation, or even the warp equation, mass is the enemy. So, the sleepy scientist offers a solution that fits perfectly with the quiet of the night. We must learn to sleep. Not just the sleep of a single night, but the deep suspended slumber of the bear or the frog. We must master the art of hibernation. In the medical world, this is known as torpor. It is a state where the metabolic rate drops drastically. The heart slows to a faint rhythm, beating perhaps only once or twice a minute. The body temperature cools, hovering just above freezing. The cells stop dividing. The demand for oxygen plummets. Imagine the crew quarters of our starship. There are no beds, no galleys, no gyms. Instead, there are rows of pods, glowing softly in the dark. Inside each one lies a traveller, floating in a suspension fluid that protects them from the g-forces of acceleration. They are connected to tubes that feed them nutrients and remove waste, but they do not breathe in the conventional sense. An oxygenated liquid circulates through their lungs, or perhaps their blood is oxygenated directly by machines. To the outside observer, they look like they are dead. There is no movement, no flutter of the eyelids. But deep inside the brain, a tiny spark remains lit. The subconscious is suspended in a grey, dreamless fog. They are waiting. This technology allows us to shrink the ship. We do not need vast hydroponic gardens or libraries. We just need the pods and the power to keep them cold. The crew does not age, or rather, they age so slowly that a 10-year journey costs them only a few weeks of biological time. They cheat the clock, not through relativity, but through biology. But there is a psychological weight to this long sleep. When you enter the pod, you are saying goodbye to the world you know. You close your eyes on Earth, and when you open them, everyone you knew might be older or gone. You are skipping the boring parts of the journey, yes, but you are also surrendering your vigilance. You are trusting the ship completely. For the duration of the voyage, the human soul is offline. The ship is a tomb flying through space, carrying the seeds of life in a state of suspended animation. It is a profound act of faith. You trust that the power will not fail. You trust that the AI will wake you. You trust that the destination is worth the oblivion. And what happens to the mind during that long silence? Do we dream? Some scientists worry that the human brain cannot handle years of sensory deprivation. They fear that even in torpor, the mind might wake up and find itself trapped in a paralyzed body, drifting into madness. To prevent this, the sleep must be absolute. We might need to edit the memory of the sleep itself, so that for the traveller, the journey feels instantaneous. One moment, the lid of the pod is closing on Earth. The next moment, it is opening under the light of a new sun. The years in between are simply gone, stolen by the void. This creates a strange discontinuity in life. You become a time traveller, jumping from island to island of consciousness, skipping the oceans in between. Your life is no longer a continuous stream, but a series of distinct episodes separated by great gulfs of darkness. But there is a beauty in it too. It is the ultimate rest, a sleep so deep that it heals the weariness of being human. A pause button on existence. As you lie in your bed tonight, you are practicing for this. You are letting go of the world for a few hours, trusting that it will be there when you wake. The interstellar traveller just does it for a little longer. When the pods finally open and the crew stumbles out, gasping the first breath of alien air, they will face a reality that is perhaps the most difficult part of faster-than-light travel. It is not the gravity or the radiation. It is the loneliness of time. We have spoken about how relativity warps time and how wormholes might connect different moments in history. But even without complex paradoxes, the simple act of travelling to the stars creates a disconnect. It fractures the human species. Imagine a colony ship leaving Earth for a planet 50 light years away. They use a warp drive that gets them there in just 1 year of ship time. For the crew, they have aged 1 year. They are still young. They remember the slang, the music, and the politics of the Earth they left. But on Earth, 50 years might have passed. Or if they travelled at normal speeds, thousands of years. Even with FTL, if there is no way to send a message back instantly, the colony becomes an island. They land on the new world, they build their dome, they plant their crops, they start a new branch of civilization, but they are cut off. If they send a message to Earth saying, "We arrived," and that message travels at the speed of light, it takes 50 years to get there. Earth sends a reply, it takes 50 years to come back. A conversation where "hello" and "how are you" are separated by a century is not a conversation. It is a history lesson. This means that every colony we plant becomes a separate experiment in humanity. Isolated by the lag of light, they will evolve on their own. Their language will drift, their values will shift, their technology will diverge. On Earth, we are used to a global culture. The internet connects us all. But in a galactic civilization, There is no internet. There is no simultaneous now. There is only the local now of your planet. Over centuries, this drift could become profound. The humans on the colony world might adapt to higher gravity, becoming shorter and stronger. They might adapt to a dimmer sun, their eyes becoming larger. They might develop a culture that values silence and patience, shaped by the empty sky above them. Meanwhile, Earth might change in unrecognizable ways. If a ship returns from the colony 300 years later, the crew might find that they are no longer human in the eyes of their ancestors. They might be treated as aliens. They might be carriers of forgotten diseases or forgotten ideas. This is the speciation of the stars. The distance between worlds acts like the oceans between continents on Earth, allowing new species to evolve in isolation. We would become not one humanity, but a family of humanities, scattered across the dark, remembering each other only as myths. It brings a melancholy tone to the dream of space travel. We go to the stars to expand, but in doing so, we scatter. We lose the tightness of our bond. We become strangers to our own kin. But perhaps this is necessary. A single basket is a dangerous place for all the eggs. By becoming a scattered species, an archipelago of humanity, we ensure our survival. If a catastrophe strikes Earth, the colonies survive. If a plague hits the colony, Earth remains safe. The silence between the stars becomes a quarantine, a buffer that protects the species as a whole, and it adds a richness to the universe. Imagine a future where a traveller can hop from world to world, and on each one, find a different version of what it means to be human. On one world, a society of philosophers living in cloud cities. On another, a rugged clan of miners who have forgotten the name of Earth. On a third, a civilization merged with machines. The warp drive is the boat that lets us visit these islands. It allows us to stitch the quilt together, even if the patches are different. We have spent our journey looking outward, imagining ourselves as the travellers, the builders, and the pilots. We have pictured our own ship sliding through the diamond geometry of a warp bubble. But there is a thought that inevitably follows us into the dark, a question that has haunted humanity since we first realised the stars were suns. If the laws of physics allow us to build these ships, has someone else already done it? For 60 years we have pointed our radio telescopes at the sky, listening for a whisper. We have scanned the frequencies of hydrogen, hoping to hear a pattern, a sequence of prime numbers, a greeting from a neighbour. This is the search for extraterrestrial intelligence, or SETI, and for 60 years we have heard only the static of dying stars and the hum of the cosmic background. The silence has been profound, but the sleepy scientist wonders, are we listening to the wrong thing? If a civilization is advanced enough to build a warp drive, they would likely have abandoned radio waves long ago. Radio is slow, it is limited to the speed of light. To a species that can cross the galaxy, in a month, using radio would be like using smoke signals to communicate across the Atlantic Ocean. Perhaps the reason the sky seems quiet is not because it is empty, but because it is filled with signals we do not know how to catch. Imagine that the galaxy is crisscrossed with tachyon beams, those faster-than-light ghosts we spoke of earlier. Imagine that the vacuum is humming with the gravitational ripples of passing warp ships. If we could build a detector sensitive enough to feel the wake of a warp drive, the sky might suddenly light up. We might see the tracks of commerce and exploration woven across the Milky Way. We might realize that the silence was never silence at all. It was just a frequency we couldn't hear. We have been standing in the middle of a busy highway, blind and deaf to the traffic rushing past us. This brings us to a concept called the technosignature. Usually, we look for Dyson spheres, giant shells built around stars to harvest their energy. But a warp drive leaves a different kind of mark. Remember the high-energy particles swept up by the bubble? The warp boom we discussed? If an alien ship were to drop out of warp near a star system, it would release a sudden, intense burst of gamma rays. To our current telescopes, this might look like a natural phenomenon, a gamma ray burst from a collapsing star. How many times have we looked at a flash of light in the distant universe and written it off as a supernova when it was actually the arrival of a traveller? It is a humbling thought. It suggests that our astronomy is still in its infancy. We are like children trying to understand the sounds of a city by listening through a thick wall. We hear thumps and rumbles, but we cannot distinguish the music from the machinery. And there is an even stranger possibility. If wormholes are possible, and if they connect distant points instantly, an advanced civilization might not travel through the space between stars at all. They would step from doorway to doorway. They would be a point-to-point civilization. To them, the space between solar systems, the wilderness, where we are looking for signals, would be flyover country. They would have no reason to broadcast radio waves into it. They would live entirely within their network of gates, invisible to anyone stuck on the outside looking up. So, the silence of the night sky is not a discouragement. It is a mystery. It tells us that we have not yet learned the language of the grown-up galaxy. We are still shouting over the fence, while the neighbours are using fibre optics. As you rest, let this idea expand the horizon of your imagination. The emptiness above is not necessarily empty. It might be teeming with a conversation too fast, too subtle, and too advanced for us to perceive. We are not alone in the dark. We are just waiting for the moment we learn to tune in. If the galaxy is indeed full of faster-than-light travellers, why haven't they visited us? Why hasn't a warp ship appeared in Earth's orbit, lowered a ramp, and welcomed us to the club? This is the Fermi paradox. Where is everybody? There is a darker theory that answers this, one that fits the quiet mood of our journey. It is called the dark forest hypothesis. Imagine the universe is a dark forest at night. It is full of hunters. These hunters are civilizations. In this forest, survival is the only rule. Because light speed, or even warp speed, limits communication, you can never truly know the intentions of another hunter. You don't know if they are peaceful or hostile. You only know that they are growing, consuming resources, and potentially dangerous. In such a forest, the safest move when you see another life form is to stay silent. Or, if they reveal themselves, to eliminate them before they can eliminate you. In this view, the silence of the galaxy is not empty, it is terrified. Civilizations that broadcast their location, like we are doing with our radio signals, are the ones that get eaten. The survivors are the ones who learn to hide, to cloak their warp signatures, to slip through the dark without breaking a twig. It is a chilling thought. It suggests that the reason we haven't seen warp drives is that anyone smart enough to build one is also smart enough to use it quietly. But there is a gentle counter-argument to this fear, one that the sleepy scientist prefers. The dark forest assumes that resources are scarce. It assumes that civilizations fight over planets and stars. But if you have the technology to bend space-time, to build wormholes, to harvest the energy of black holes, you do not need to fight for land. You have the universe. A civilization that can build a warp drive has effectively infinite energy and infinite space. They can access billions of uninhabited star systems. They can build ring worlds and Dyson swarms. They have no economic reason to invade a small wet rock like Earth. We have nothing they need. To them, we are not a threat, and we are not a prize. We are a nature reserve. Perhaps there is a prime directive, a rule among the stars that says, do not disturb the cradle. Maybe they are watching us right now, hidden behind their cloaking fields, waiting to see if we survive our own adolescence, waiting to see if we stop fighting each other long enough to look up. This theory transforms the silence from a threat into a waiting room. We are in the nursery of the galaxy. The adults are walking softly in the hallway, letting us sleep, letting us dream, until we are ready to wake up and join the conversation. It suggests that the barrier to entry is not just technological, it is moral. To join the community of stars, perhaps we must first prove that we can wield power without destruction. We must prove that we can handle the fire of the warp drive without burning down the house. So when you look at the stars, do not feel afraid of the silence. Feel protected by it. It gives us time. Time to grow, time to learn, time to become the kind of species that deserves to travel faster than light. We are alone for now, but it is a constructive solitude, a quiet space where we can decide what kind of travellers we want to be. We are nearing the end of our thought experiment, and we must confront the magnitude of what we are proposing. We have talked about warping space, slowing time, and punching holes in reality. We have talked about harvesting the energy of stars and black holes. Make no mistake, these are the powers of gods. In ancient mythology, gods were beings who could change the shape of the world at will. They could step across oceans. They could stop the sun in the sky. If we build a warp drive, we become those beings. We become the masters of geometry. This brings a heavy weight of responsibility. We are not just explorers, we are architects of the cosmos. If we build a wormhole, we are permanently scarring the structure of space-time. We are sewing two parts of the universe together. What right do we have to change the anatomy of the galaxy? What if our tunnel disrupts the gravitational balance of a star system? What if our warp wake disturbs the nebula where new stars are being born? We are introducing human chaos into a system that has run on clockwork physics for billions of years. There is also the risk of weaponization. Any drive that can accelerate a ship to relativistic speeds is also the ultimate weapon. A warp ship doesn't need a laser or a bomb. The ship is the bomb. If you fly a starship into a planet at 10 times the speed of light, or even just 99% of it, the kinetic energy release would shatter the world. A civilization with warp drive is a civilization where every ship captain has the power to destroy a planet. How do we survive that? How do we build a society where we trust every single pilot with the power of an apocalypse? It requires a fundamental shift in human nature. We cannot take our current tribalism, our anger, and our fear into the stars. If we do, we will not last long enough to enjoy the view. We will destroy ourselves in a war of relativistic missiles. This is the great filter that many scientists speak of. The idea that civilizations destroy themselves as soon as they discover powerful technology. But the sleepy scientist is an optimist. I believe that the process of discovery changes the discoverer. To build a warp drive requires global cooperation. It requires the resources of an entire planet, the minds of millions working in harmony. You cannot build a starship in a war zone. The very act of reaching for the stars might be the thing that heals us. To look down at Earth from the window of a warp ship is to see it as a single, fragile gem. It is to realize that boundaries are lines on a map, not lines in the sand. The ethics of a god require the wisdom of a god, and perhaps the universe forces that wisdom upon us. Perhaps the physics of warp drive are so difficult that only a united, peaceful, and wise species can ever solve them. Maybe the speed of light is not just a physical barrier, but a spiritual one. A test, a lock that only opens for a species that has learned to put down its sword. As you lie there, consider this. The journey to the stars is also a journey inward. We cannot go out there until we have fixed what is in here. The stars are waiting for us to grow up, and the silence is just the universe holding its breath, waiting to see if we make it. Before we close our eyes, let us take a moment to honor the people who made this journey possible. Not the fictional captains of starships, but the real people. The ones who stood at blackboards covered in chalk dust and dared to write down the impossible. We stand on the shoulders of giants. We must remember Albert Einstein, the patent clerk who looked at a beam of light and saw the structure of the universe. He told us that the walls were flexible. He gave us the permission to dream. We must remember Miguel Alcubierre, the theoretical physicist who watched science fiction on television and asked, why not? He sat down and did the math that proved a warp bubble was consistent with general relativity. He turned a fantasy into a field of study. We must remember Kip Thorne and his students who dove into the math of wormholes and showed us that time travel and bridges across the stars were not just magic, but geometry. And we must remember the countless others, the mathematicians, the engineers, the science fiction writers, who kept the flame alive. the writers who imagined futures where we were better, braver, and farther from home. They built the mental maps that the scientists are now trying to fill in. Science is a conversation across centuries. It is a relay race. Einstein passed the baton to Alcubierre, who passed it to Lentz, who passes it to the students sitting in classrooms today. Maybe one of those students is listening right now. Maybe you are that student, or maybe you are the parent of that student. The dream of the warp drive is not just about physics. It is about legacy. It is about the human refusal to accept limits. We look at the ocean and we build a boat. We look at the sky and we build a plane. We look at the speed of light and we build a spaceship. It is in our DNA to push, to wonder, to seek. We are the descendants of wanderers who walked out of Africa, who crossed the ice bridges, who sailed the Pacific in wooden canoes. The warp drive is just the latest canoe. The stars are just the new islands. So when you think of the future, do not think of it as a cold mechanical place. Think of it as the continuation of our story. A story written by dreamers who looked at the impossible and blinked. The legacy of the dreamers is the map we hold in our hands. It is incomplete. The edges are ragged, but it points the way. And tonight, as we rest, we add our own quiet hope to that legacy. We keep the dream warm. So, where do we stand right now? Are we on the verge of launching the Enterprise? No, we must be honest. We are still on the shore. We are still playing with lasers on a table, looking for a microscopic twitch. But the horizon is brighter than it has ever been. 10 years ago, warp drive was considered a joke, a fringe topic. Today, it is published in serious, peer-reviewed journals. It is discussed at conferences. It is funded by grants. The stigma is fading. We are entering the era of warp field mechanics. We are moving from the theoretical phase to the experimental phase. We are beginning to design the first tiny, clumsy engines that might interact with the vacuum. We are finding that the energy requirements are dropping. We are finding shapes that don't need magic fuel. We are finding hints in the quantum foam. The next century will likely be the century of the prototype. We might not build a ship that carries a human, but we might build a probe. A tiny automated vessel that warps space just enough to cross the solar system in days instead of months. We might send a probe to Alpha Centauri within our lifetime. We might get that picture of a new sun. And once the first probe succeeds, the dam breaks. The impossible becomes the inevitable. It is a wonderful time to be alive and curious. We are living in the dawn of a new physics. We are watching the transition from we are stuck here to we can go anywhere. It is a slow dawn, yes. Science is patient. It checks its work. It makes mistakes. It goes down blind alleys. But it always moves forward. The horizon of possibility is expanding. Every day, the cage of the speed of light gets a little wider. Every day, the universe feels a little more accessible. So, hold on to that optimism. The problems we face on Earth, the energy crises, the resource limits, these are solvable problems. And the technologies we develop to solve them, the fusion reactors, the superconductors, the quantum computers, are the very same tools we need to build the starship. We are building the ladder rung by rung. We might not climb it all the way to the top, but we will leave it standing for the next generation, and they will climb higher. The future is not a closed door, it is an open sky, and it is waiting for us. And now we have reached the end of our journey for tonight. We have travelled from the surface of the Earth to the edge of the event horizon. We have surfed on waves of gravity and stepped through tunnels in the sky. We have listened to the silence of the dark forest and felt the warmth of the warp bubble. It has been a long voyage, but now it is time to return to the stillness of the room, to the gravity that holds you gently to your bed, to the air that fills your lungs. Take a deep breath. Feel the solidity of the world around you. It is good to have a home. It is good to have a quiet corner of the universe where the laws of physics are stable and kind. The ideas we explored tonight are vast, mind-bending, and perhaps a little overwhelming. But you do not need to carry them all. You can set them down, let them drift away like leaves on the river of time. Remember simply this: the universe is not a prison. It is a playground of geometry. It is a place where the rules are just challenges waiting for a solution. We are small, yes, but our minds are capable of wrapping around the cosmos. We are the part of the universe that has learned to dream about itself. And as you drift into sleep, know that the dream continues. Somewhere in a lab, a laser is humming. Somewhere in a university, a student is staring at an equation. Somewhere in the future, a ship is warming up its engines. The story is just beginning. I hope this journey has helped you unwind, unraveling the knots of the day, just as we hope to unravel the knots of space-time. If you enjoyed this quiet exploration of the impossible, and if you would like to join me for the next voyage into the mysteries of the cosmos, please consider subscribing. It really does help this little channel grow and reach more sleepy minds. And if you want to be notified when the next ship is leaving the harbour, tap the notification bell. It is your ticket to the stars. But for now, there is nothing left to do. The equations are balanced. The ship is safe. The stars are watching over you. Let the darkness wrap around you like a warm blanket. Let the silence be a comfort, not a mystery. Sleep well, traveller. The universe will still be here in the morning. Good night.